In this video, we're going to look at cross terms in molecular mechanics and force fields. So there's one big assumption that we've been doing when we've been describing all of these energy terms in molecular mechanics, and that can be summarized in this question. So let's look at, we have a water molecule here. We have 3 atoms, HOH. We have 2 bonds, each of them at the same bond distance of r, and we have 1 bond angle, the HOH bond angle of theta. So we've been assuming that the energy of this system would be the bond energy of each of these 2 bonds plus the angle energy of this angle, and those are each quadratic potentials around their minimum, around REQ and around theta EQ. But the question comes up, now if R changes, does theta not change, or does theta EQ change? So I'll write this as theta EQ to be consistent. So does theta EQ change? And similarly, if theta changes, does REQ change? Does the value of one of these degrees of freedom affect the equilibrium value of the other? And in molecular mechanics so far, we've been assuming that they didn't. So to address this question, let's look at a second order Taylor series approximation for the energy of the system around the equilibrium bond length and around the equilibrium angle. Okay, so this energy of this system would be E of RA. And I'm not going to be concerned right now with the fact that there are 2 of these bonds. I'm just going to assume that there's one of them. The other one's going to be equal as well. But the math ends up working out the same. So E of R theta is equal to, okay, so the first term would be the 0 order term. E naught of R will be E of REQ theta EQ. So that'd be the 0 order approximation, is it's just the equilibrium. And in fact, I should have these as approximates as well. And that this is an approximate Taylor series around this term, around those coordinates. Okay, first term would be 1 over 1 factorial, which is just 1 of first derivative of partial derivative of E of R theta. Sorry, I have A in my notes, so I'm going to be writing that a lot. E of R theta with respect to R, evaluated at R equals REQ, times RE minus REQ. Okay, first order term with respect to R, makes sense. Then we have a first order term with respect to theta. Put that parentheses on the inside. Partial derivative with respect to theta, evaluated at theta equals theta EQ, times theta minus theta EQ. Okay, so that's the first order term with respect to theta. All right, so that's the first order Taylor series. So now going to second order, we include the second derivatives and the cross and the mixed partial derivatives. So first term, second derivative of E with respect to R, evaluated at R equals REQ, R minus REQ squared, plus same term for theta, E of R theta with respect to theta, theta equals theta EQ, theta minus theta EQ squared. Okay, thus far it all looks good. These are all terms we've accounted for because in our derivation of the terms with respect to R and theta, we've included these terms as well. But now there comes up a cross term when we're looking at the Taylor series of the 2 variables here. We have second partial derivative, or the mixed partial derivative of E with respect to R and theta, with respect to R with respect to theta, evaluated at R equals REQ and theta equals theta EQ, times R minus REQ times theta minus theta EQ. Okay, so now going through these terms, collecting them up. This is defined to be 0. The energy is defined to be 0 at the equilibrium bond length and bond angle. The first derivative at the minimum with respect to r, so the first derivative of r evaluated at the equilibrium is the minimum of the parabola. That partial derivative is 0 because the tangent line is flat. And that makes this term 0. Same thing for theta. The tangent line of the energy with respect to theta at theta equals theta equilibrium is 0. This term is our bond energy, ER. This term is our angle energy, E theta. So this is KB R minus REQ squared. This is KA theta minus theta EQ squared. But this term is what's new, and this is what we would call a cross term. This is the interaction between the bond length and the bond angle. So this term here, this second derivative of E with respect to R and with respect to theta, that's what we would call, for example here, we'd say the second derivative of E with respect to R with respect to theta evaluated at each of them equaling their equilibrium value is equal to K A R. So I would say that KAR is a bond dash angle cross term spring constant or force constant. So that would have units of, if our energy is kcal per mole, it'd have kcal per mole times angstroms times radians if our angle is measured in radians. So notice that for bonds, the force constant was kcal per mole angstrom squared. For angles, it was kcal per mole radian squared. This is the cross term, so it's kcal per mole per angstrom per radian. Okay, so what we basically assume and what we hope is that KAR is approximately 0 and that we can set it to 0 for most force fields. So if not, then what we have is a cross term where we would have, let's see, we would have EAR would equal KAR times R minus REQ times theta minus theta EQ. So we'd have a cross term there where each of their deviations away from their equilibrium value is scaled by this cross term value there, which is effectively changing what theta EQ and REQ are as R and theta change. Okay, so cross terms can in principle appear for any kind of bonded interactions that you have. So we could have bond-bond cross terms. We can have bond-angle cross terms. We can have angle-angle cross terms, etc. for there. So two different bonds, if these bonds weren't the same, if one were to have different parameters than the other, then we could have a cross term between them. We could have cross terms between various angles in a molecule, like the cross term between the HCH and HCO bond angle in formaldehyde that we looked at earlier. But overall, what you're trying to do here is you're taking a bigger Taylor series of the energy with respect to your internal degrees of freedom. So what you're hoping for overall is a more accurate force field. But when doing so, the accuracy of a force field is always a trade-off between how long do you want it to take to compute and how accurate do you want it. So for people who want just a quick and easy and don't want things to be as computationally demanding, they're usually fine without cross terms, and they'll usually do the simpler force field. But if someone is super interested in accuracy and they want to get a force field that is as accurate as they can get, they might include these cross terms or even various higher order terms with respect to individual terms. They might include a cubic and quadratic term with respect to the bond lengths or bond angles. But lots of options there are, but what I've displayed thus far in this chapter is the basics, the elements that pretty much all force fields have, and that any higher order terms try to improve upon, like cross terms or having more advanced energy function forms.